Let's discuss chapter number 2 of power system, electricity and magnetism. So the first thing that we are going to discuss is Fourier series fundamentals. I believe we have discussed Fourier series in other classes as well. Now in this specific course, you may not be really using Fourier series. The only reason I'm discussing Fourier series in this course is um, when the voltage is generated through generators, generally it is assumed that it is a perfect sinusoid AC voltage, and many times it is not. So the only reason we are discussing Fourier series is Fourier series gives us the information that any any periodic waveform which is non-sinusoidal is always comprised of three components. And what are those three components? Those three components are that it may have a DC voltage or an average value which may be non-zero if the waveform is not symmetric about x-axis. So that's one of the component. It must have a sinusoidal component with the same frequency as your original periodic signal. So for example, if your original periodic signal is a square wave with a frequency of 1 kilohertz, there must be a sinusoidal component in making that square wave with the same frequency, that is 1 kilohertz, and that component is called fundamental component. And the third component that is present to make that periodic waveform, again assume it's a square wave, so to make the square wave is or are multiple sinusoidal waveforms which have frequency which is multiple of the frequency of the fundamental component, or in other words, their frequency is multiple of the frequency of your original waveform, and those components are called harmonics. So each periodic waveform is comprised of a DC component which may or may not be zero, fundamental component that is a sinusoidal with the same frequency as the original waveform, and harmonics. Now some of the harmonics may be present, some of the harmonics may not be present. And once you do the analysis, then you know which harmonics are present and which are not present. Now in this course again, we are not going to be doing the analysis, we're not driving any equation of for a series of any waveform. Again, this is just for the information purpose that if you see a non-sinusoidal waveform which is periodic, always remember that three components are there, or not three components, I mean harmonics are many harmonics, infinite harmonics, but in general you have three components, which is the fundamental waveform, the DC component, and harmonics to create that periodic non-sinusoidal waveform. Now there are three different equations or three different ways you can calculate the Fourier series of any function, and I think I'm introducing only the first one, which is called the trigonometric Fourier series. So this is the trigonometric Fourier series right here. Xt is your original waveform, periodic waveform, A0 is your DC component, and then n is, if n is 1, that is your fundamental component, and if n is 2, 3, 4, those are your harmonics, the second harmonic, third harmonic, fourth harmonic, so on and so forth. So observe that n omega naught is the frequency of the original waveform. So when n is 1, your component has the same frequency as the original waveform, that is the fundamental component has the same frequency as the original waveform. You have two components, cosine and sine. This is called the trigonometric Fourier series. When n is not 1, it is 2, 3, 4, then your frequency of the sinusoidal function is going to be 2 omega naught, 3 omega naught, and those are the harmonics, that is the frequency of the harmonics are multiple of your fundamental component. An and bn are the coefficients or the magnitude of your harmonics and fundamental component, and as the number of harmonic increases, that is 5 omega naught, 6 omega naught, 7 omega naught, their magnitude goes down. So although this series is an infinite series, but after a specific number of harmonic, the contribution of harmonics becomes pretty much non-essential. So we ignore those harmonics above a specific harmonic value. So this is again just a theoretical background of what Fourier series is and why do we use it. And I'm putting one example. If we do the derivation of the Fourier series of a square waveform, then we're gonna get this equation. V peak by 2 is the DC component right here, and then you have all the an are 0 over here. So when you do the derivation, all of the values of an will turn out to be 0, and you have only bn values, which are 2 vp over n pi, and this value actually is only valid for n is equal to 1, 3, 5, 7. That is the fundamental component, third harmonic, fifth harmonic, seventh harmonic, so on and so forth. So as you plot this equation and you keep adding harmonics, you will see that your waveform becomes more like a square wave. As many harmonics you're gonna add, the waveform become more squarish. If you don't add more harmonics, then the waveform will not be as squarish as you want it to be. And then I'm showing you one example that if the square wave peak value is 10 volt and the frequency is 100 hertz, then if I add up to the 9th harmonic using this equation and I plot it using MATLAB, then this is what you're gonna get. Observe, you have noise over here and noise over here, because again you're not adding many harmonics. As you increase the number of harmonic, you go up to 21 right here, then again you still have noise, but it start becoming more squarer. And as you go and add 100 components, observe it has become quite a square like. It's still a little bit roundish, but it's possible that I'm not using a lot of points to plot this graph, but this is pretty squarish waveform from 0 to 10. So this is just a basic discussion of Fourier series. The only thing again you need to be aware of in this course specifically is what is harmonic, what is the frequency of harmonic, what is the fundamental component, DC value, and the basic idea of Fourier series, that when you add all these things, basically you get your original signal back. I think there is an example 2.1, that we have a sinusoidal voltage which is affected by noise, and it becomes non-sinusoid because harmonics basically whenever some signal becomes non-sinusoid, that means you always have harmonics. As you can see over here, harmonics. Of course, if there is no harmonic, then your signal is going to be a perfect sinusoidal waveform. So the question is, if the 13th harmonic frequency is 223 hertz, what will be the fundamental frequency? Which is pretty straightforward. 13th harmonic frequency will be 13 times the fundamental frequency, so you can get the fundamental frequency from that. Next video we're going to discuss Faraday's law of electromagnetic induction.